This is a relatively short lecture where we'll discuss input and output devices in a computing system. One of the important things for input and output devices is that we need to control these devices. The instructions that we use to control the input and output devices are called I/O commands. And the I/O device are managed by an I/O controller hardware. And this controller hardware will transfer the data to and from the device. And then it has to synchronize its operations with the software that's running in the computer. Command registers are registers that when I write to those registers, they will cause the I/O device to do something. For example, I can command a display to go completely black or something like that. And the status register is a register that is used to indicate whether the device is what the device is doing, or if there was an error in the device. So typically a status register is read and the command register is written to. An example of the status register is the ready status in the display device in the Lab 5. And then we have data registers. In the data register can write to the data registers, which means that I'm transferring data to the device, or I can read from the data registers, which means that I am transferring data from the device into probably some register, or in some systems I could be doing a transfer between the device and the memory. But if I'm reading a data register, most likely I am doing a transfer between a data register in the device and a register in my processor. There are two ways that I can access input and output devices. One of them is called memory mapped I/O, and the other is called an I/O instruction. In memory mapped I/O, what happens is that there are some special memory addresses that are used to access an I/O register. So the address decoder will capture that those are I/O accesses. So from the point of view of the assembly program, it's not different than accessing memory. I do load from a specific address that has been predefined to be a memory mapped I/O device, and that load that from the point of view of the assembly program looks like it's just a regular load will actually be bringing data from an input-output device. Similar to a store, if I want to write into the command register of a device and that device has been mapped to memory, it's a memory mapped I/O device, what I'm going to be doing is doing a regular store. In that store, instead of going into the memory, we'll go into the I/O device, and the kind of taking the operation from going to memory and making it go to the I/O device is done by an address decoder. Sorry. The operating system will ensure that the I/O mapped addresses are only accessible to the kernel. A user cannot talk directly with a device. A user has to always ask the kernel for a service, and the service will be, for example, to print an integer to the terminal. You are used to make those calls in your programs in assembly. When you are doing a call, an eCall to print, for example, something to the display, you are asking the kernel to access an I/O device for you. Similar when you ask, for example, the kernel through an eCall to read an integer from the keyboard. There are an alternative way to access I/O device instead of mapping them to memory is to access through I/O instructions. In this case, there is a separate set of instructions that is specialized in accessing the I/O device. These instructions can also only be executed in the kernel mode. And for example, the x86 processors from Intel, they all have I/O instructions and the RISC-V does memory mapped I/O. Another topic that we're going to cover in this short lecture is the connections with the input-output devices. So the processor will be connected to this memory and input-output interconnect network. There is a cache. We haven't studied cache yet, but it's one of the units that's coming up this term. And then there is the main memory that is connected to the memory interconnect. And there might be one or several controllers for I/O. For example, I can have a separate controller for the disks. I may have a controller for some kind of graphic output. I may have a controller for the network. All those controllers are controlling different I/O devices, and they can interact with the processor through interrupts. This interconnect that connects with the memory and with the other devices can be a bus, and a bus is a set of parallel wires, and it can also be a pair of serial wires, or it can also be some kind of interconnected switch. So what is a parallel bus? So if I want to transmit a single bit between, for example, the processor and the memory, or the process and an I/O controller, the single bit will be 1 wire in my system. If I want to transfer 2 bits, that will be 2 wires in the system. And if I have 32 bits, there will be 32 wires. If I have 64 bits, there will be 64 wires. So this is what we call a bus. Besides the data lines that I have in my bus, I also have address lines, and if I have a 32-bit machine, there will also be 32 address lines, and then I have additional lines that are the control lines. For example, when the processor is about to execute an instruction, the processor has to read that instruction from memory. To read the instruction from memory, the processor will put the address that it wants to read from into the address bus, and will specify in the control lines that this is a memory access, that is a read or a load. If the processor wants to execute a store, the processor will put the address of the position to be stored in the address lines, the value to be stored in the data line, and the control lines will specify to the memory that this is a write or a store. There is the processor memory bus, and then there are I/O buses. So this is a picture that illustrates the organization of a typical computer system. So you have the CPU, that's where our processor lives. And then there is a host bus. The host bus connects with one or several layers of caches with the memory and with a bridge. This is what's called the host PCI bridge. And this bridge then connects with another bus. The PCI stands for Peripheral Component Interconnect. So those PCIs are the devices that will connect to the peripheral devices. And I may have what is called PCI buses, that is after one of those bridges, I may connect several devices to that secondary bus. And ISA is the industry standard architecture. So a PCI host bridge will look like something like this, where I have the PCI bus on one side and the host bus on the other side. And here I have the host bus interface, and I have several different components that form this bridge. I put in this figure up just to illustrate that there is quite a bit of complexity into the construction of such a bridge. One of the things that may be now familiar to you is this block on the bottom here, that is the interrupt controller. And the interrupt controller for this PCI bus will take interrupts from devices that are connected to this bus and decide whether it needs to bring this interrupt, whether it can handle the interrupt itself, or whether it needs to bring an interrupt to the main processor through the host bus. Here is a picture from the IBM Power 4 interconnection. IBM Power 4 is now 5 generations behind the current generation. We are currently have the Power 9, and my research group is working with IBM on the delivery of Power 10, which we expect that it will come in the future. And one of the features of Power 10 is that it has this unit called the Matrix Multiply Accelerator Unit. And my research group, in collaboration with IBM TJ Watson, with the University of Campinas in Brazil, and with the IBM Software Laboratory in Markham, is working on the delivery of the software for that unit. That is the compiler that will generate code for that unit. But here, this is the IBM Power 4. Power 4 had 2 processor cores. There is a switch that connects the caches to the Power 4. Then there is something called the fabric controller. And then this fabric controller, which is a fairly sophisticated network, will connect it with several of the other bridges. And my I/O bus actually appears right here. This is where my input and output devices will be connected in this processor. We need to talk about bus synchronization. So most buses today are synchronous buses, which means that there is a clock for the bus. So a clock, as we understand from earlier units, is a signal like this that repeatedly moves from high to low and low to high at a very regular intervals. So what the clock does, it sets a time for when things can happen. So if the processor and the host bus is synchronous, then there will be specific times for accesses to memory and how long those accesses should take, or how many cycles they should take in terms of the clock cycle. If I have an asynchronous communication with a bus, then I have a handshake that is request acknowledge control lines for handshaking. So typically, such buses will have signals that says, I am ready, the data is valid, here's the data, here is the clock signal, etc. So I can have several different signals going back and forth between devices to complete the operations when I have an asynchronous communication with a bus. Here is a typical x86 PC I/O systems. What I have here is that the main processors are up here. I may have a single processor or a dual processors. Nowadays, pretty much every machine has multiple processors. And then I have a memory controller hub that is called the North Bridge. And then I have the I/O controller hub down here that's called the South Bridge. As you can see, your memory, here represented by dual inline memory modules, is connected to the North Bridge, that's the memory controller. I can have a PCIe that is a peripheral controller interface express that is maybe connected directly to the North Bridge, but I may have other PCIes that may be slower. So this one will be a fast one. Slower ones may be connected to the South Bridge, and I may have my disks, keyboard, mouse, etc. connected to my USB ports connected to the South Bridge. We have to also talk about I/O management. I/O is mediated by the operating system. User programs do not handle I/O. I may have multiple programs share the same I/O resources. I need to have protection and I need to have scheduling. So I cannot have multiple user programs accessing the I/O devices. The I/O, the input-output devices cause asynchronous interrupts, so they use the same mechanism as handling exceptions. And I/O programming is fiddly. The operating system will provide the abstractions to the programs so the programs can use the I/O device. In your operating systems course, you're going to learn more about how to handle input and output devices and how the processor communicates with them.